Welcome back to week 7. This week we'll be covering chapter 31 on light quanta. So this week you'll have this lecture on chapter 31. You have your second test this week covering chapters 27, 28, and 29. You won't have any homework this week, but your homework next week will have some questions based on this chapter. Your lab this week is to watch a video on quantum theory, and then your discussion will also be based on this video. Since you have a video to watch, that takes a little bit of time. It's okay if your discussions are turned in a little bit late this week. In this chapter, we'll cover how quantum theory originated. We'll talk about quantization and Planck's constant, what the photoelectric effect is, how light behaves like a wave and a particle, and then how some experiments such as electron slit experiment and electron diffraction show that light has wave and particle-like properties, and then we'll talk about what the uncertainty principle is. First, we're going to look at how the quantum theory started up, and in 1900, physicist Max Planck hypothesized that when a warm object emits energy, that the energy isn't just lost continuously or in a continuous stream, but it's given off in discrete bundles or lumps, which he called quanta. We now call these bundles of light photons. So for light particularly, we call these bundles photons. And the laws that describe the property of these tiny quanta or photons is called quantum physics. Quantization is the idea that the natural world is granular rather than continuously smooth. So again, that these bundles of light energy are in these packets rather than, in bundles rather than given off continuously. We call that quantization. And quantum physics states that in the micro world of the atom, the amount of energy in any system is quantized, so not all values of energy are possible. And so what this means that, like, if you have a fire that's burning, that it can only burn at certain temperatures, and not every temperature in between. Now, this really doesn't seem logical to us, because we would say that we could measure the campfire and we could get every single temperature in between. But we're only looking down to a certain scale of temperature. So when we're measuring something and, we measure 0.1, 0.2, 0.3 degrees Celsius, these quanta that we're talking about are measured at the level of the photon. And so there's such a small level that if you were to get down to that small level, then the temperature could only be in discrete amounts and not every value in between. And again, that's because you're looking at such a small level, and we don't necessarily see that in our day-to-day lives because we're looking at a much larger scale. Now, the quanta are tiny bundles of light, in general electromagnetic radiation. These tiny bundles, again, are called photons, and the energy of each of these quanta or photons is given by the formula that E, or energy, equals h times f, or frequency, and h is what they call Planck's constant. And so again, light's not emitted continuously, but rather is a stream of photons, and each photon is throbbing at frequency f and carrying a total energy of this Planck's constant times f. So the energy of each photon is equal to this certain value h, which is always the same, times the frequency of the light that you're talking about. So what this means is that if you have something with a very low frequency, then the energy is going to equal this set value h times that low frequency, which means that that particular photon will have a very low energy. So for example, microwaves have a low frequency, and therefore the energy of each microwave photon is very low. So when you get hit with microwaves, they're not doing a lot of damage to your body because there's a really low energy per photon. UV light, on the other hand, has a higher frequency, and therefore it's going to have a higher energy per photon and can do more damage to your body. X-rays have even higher frequencies, and they can do even more. They have even more energy per photon and do even more damage. Before we get into the photoelectric effect, let's just We'll briefly go over these terms just so we're clear on the definition of these. And quantization is the idea that the natural world is granular rather than smoothly continuous. And a quantum is any elemental particle that makes up matter or carries energy. Next, we'll take a look at the photoelectric effect, which shows that when light shines on metal, it's capable of ejecting electrons from certain metal surfaces. And it shows us a model for how matter is radiated off surfaces. And it was hypothesized by Max Planck, again in the early 1900s. So essentially what the photoelectric effect is that when you shine a light down onto metal, the light will eject electrons. And if you have more light, then you'll have more electrons ejected. They're all going to have the same kinetic energy or the same energy. So shining more light doesn't mean that more energy is given off, just that there's more electrons, all with that same energy. So when we look at light, there's been this long-standing debate of whether light is a particle or wave. So all the way back to the time of Plato in the 4th and 5th century, he felt that light behaved more like a wave. And then the Pythagoreans thought that light behaved more like a particle. So there's been this debate on whether light is a wave or a particle. Now, in theory, it should be easy to distinguish because particles move in straight lines unless they're acted upon by a force, and waves can travel through openings and diffract or bend. So as we've seen with like sound, it can go through a doorway and curve around the doorway, so that those waves can bend, and light behaves like both of these. We'll cover in the next few slides some of the experiments they've done to show how light is a particle, and how light is also a wave. Now, if you were to look at light as a wave, you would expect that low-frequency light would eventually build up enough energy to eject electrons. But what we see, however, is that the low-frequency light, no matter how long you shine it on the metal, will never eject electrons. Once you get the frequency high enough to eject the electrons, then the electrons are emitted instantaneously, and they're emitted at just the same quickness as if you had a high frequency light. So the high frequency light, the higher the frequency light, you're going to have more electrons ejected. But the second you turn on that light, if the electrons are going to be ejected, they're ejected at the same time with a high frequency light or a low frequency light. And we would expect with a wave that it would take more time for that weaker light source to build up to be strong enough to eject electrons. But again, they eject electrons at the same rate, just more electrons are ejected with the stronger light. So you can see the photoelectric effect when you take a piece of metal and you give it a negative charge. So you have your battery here hooked up to a wire and hooked up to your metal. And so you have a negative charge on this end, and then when you shine the light on there, electrons are given off of that, or ejected from that metal, and they're attracted to the positive end over here. And what we can do is we can see the current flowing through this wire, and we can use that current to calculate the energy of the ejected electrons. So Einstein took all these ideas of what happens when light is shown onto metal and electrons are ejected, and put this all together into the concept of the photoelectric effect. And so what he determined from all this is that light is a stream of particles or bundles of energy called photons, and one photon is completely absorbed by each electron ejected from the metal. So absorption is all or nothing, which is why we see that low intensity light does not, or low frequency light does not eject any electrons, and then higher frequency light can eject electrons. So it's all or nothing, depending on whether the frequency is high enough, and it is immediate. So there's no delay as you would expect there to be if there was a wave energy buildup. So if it was a wave, you'd expect the energy to build up and have somewhat of a delay, and we don't see that delay at all. And then the number of photons in the light beam affects the brightness of the whole beam, and the frequency of the light controls the energy of each individual photon. Okay, so what can we learn from the photoelectric effect? Essentially, it proves conclusively that light has particle properties. Now, keep in mind that we've also seen that light conclusively has wave-like properties, such as we see with diffraction or light bending like a wave. So we'll go into some of the wave-like properties of light here coming up, but just keep in mind with the photoelectric effect, we see that light definitely has particle-like properties. Let's go ahead and do a review question. In the photoelectric effect, the brighter the illuminating light on a photosensitive surface, the greater the, velocity of ejected electrons, number of ejected electrons, both A and B, or none of the above? And the answer is number of ejected electrons. So remember, the speed of the electrons does not change at all, but when you have a brighter light, it just means that you have more electrons. So wave-particle duality just means that waves have that light has properties of both a wave and a particle, as we've been talking about. So a photon behaves as a particle when it's emitted by an atom or absorbed by a photographic film or other detectors. So as we see with the photons bouncing off of a metal surface, it's behaving as a particle, but it behaves as a wave when it's traveling from a source to the place where it's detected. So in this sense, light is both a wave and a particle. So we've seen in the past chapter the double slit experiment, where light passes through two openings, and when that wave essentially hits these openings, we see the wave diffract or bend around those openings. And what we end up with from the interference, where sometimes the crests meet, and you get a higher crest, and sometimes the crest and the trough cancel out, and you get a low point in the wave. You see this pattern of light and dark and light and dark. And so this is what we would expect to see if light were behaving as a wave. Okay, so what they found is that if you were to dim your light source so that only one photon at a time could get through those double slits, that you'd see those photons start hitting in what sort of appears to be these random places. But then the more photons that hit, so this would be the light for a very short amount of time, the more photons that hit, you start to sort of fill in these patterns. And what we see is eventually the same interference pattern of light and dark that we would expect to see with a wave. So essentially this is showing us that light definitely is a wave. So what we can take away from this is that a photon behaves as a particle when it's being emitted by an atom or absorbed by a photographic film or other detectors. And it behaves as a wave when it's traveling from a source to the place where it's detected. The photon strikes the film as a particle, but travels to its position as a wave that has interference. Now, a French scientist named de Broglie in the 1920s asked the question, if a photon of light has both wave and particle properties, then why can't a material particle, one with mass, also have both wave and particle properties? So something like you. And his work on this later earned him a Nobel Prize. And what he found was that every particle of matter is associated with a corresponding wave. So everything, whether it's an electron, an atom, or you, or a planet, has a wavelength related to its momentum, which is given by the formula wavelength is equal to h, Planck's constant, over momentum. So what this means is that if you have something with a very large momentum, so if this number down here is very big, if you think of dividing a small number by a very, very large number, you're going to get a very, very small number. So that would mean that something with a large momentum will have a very small wavelength associated with it. Something with a very, very small momentum will have a very large wavelength associated with it. So for example, something with a large mass and moderate speed has a very high momentum. And what momentum is if something is moving, it's sort of that energy and movement that it has. So if you think of a rock rolling down a hill, a really heavy rock would be hard to stop rolling, and that fact that it's hard to stop moving is because it has a lot of momentum. It wants to keep moving. You think of a very small rock rolling down a hill, you could stop that pretty easy, but a big boulder rolling down a hill, you're not going to stop it because of its high momentum. So things with high momentum, like that big boulder, like yourself, or any other thing really that we can see, is going to have a very small wavelength associated. In fact, a wavelength that's so small that you're not even going to notice it. So you don't see people out there moving around in wave-like patterns. Something much smaller, like an electron, has a much lower momentum. So this number down here is small, which means that you're going to end up with a large wavelength. And so for these objects, things like an electron or a photon or things down at the quantum level, very, very small things, have a much higher wavelength. And so things like diffraction or the wave-like properties are very noticeable. A scientist named Heisenberg determined that since quanta have wave-like properties, when we try to measure them at a particular point, we alter them. And this is because waves cannot be squeezed into a point in space or limited to a single instant in time. So waves move through space and time, and if we try to measure them at one space at one single time, then we are changing them from what they would normally be. There's therefore uncertainty in all measurements, again at the quantum level, because by measuring things at the quantum level, we change things, and this is known as the Heisenberg uncertainty principle. Now, Heisenberg's uncertainty principle only applies to things at the quantum level, or to what they call quantum mechanics, looking at things at the quantum level. It doesn't apply to things at the larger level. So for example, working in a lab, things that we deal with for the most part on a day-to-day level, we can measure with a great deal of certainty because the amount of, by us measuring it, changing things at the quantum level is so minute compared to the measurements that we're doing that we're not altering it enough to really alter our end results. So again, the uncertainty principle just applies to quantum mechanics. That's the end of our week 7 lecture. And just in case you didn't know, we only have 2 weeks of new lecture left. That will be in week 8 and week 9. During week 10, we'll do a review week, and then week 11 will be your final. So we are quickly approaching the end. Great job to everyone. Try to stay motivated in these last few weeks here. The end is in sight. So good job, and keep it up for the last little bit of the course here. If you have any questions as you're going throughout the week, as always, feel free to let me know, and I will be in touch with you again in week 8.